Thank you, everyone, for attending this booth talk at Patheon. I'm going to talk about the Patheon Quadrant2, which is our approach on physicochemical analysis and molecular modeling for polysoluble compounds, specifically BCS class 2 and class 4. So our approach, Quadrant2, is our solubility enhancement approach, which basically utilizes a fundamentally different way of looking at solubility enhancement. It's a multi-technology approach. We look at the physicochemical characteristics of your molecule and we do a assessment of which technology would work. We have a global multi-site centers of excellence in Patheon, and we basically use focus centers of excellence which are available in our network to advance your molecule. So I'll give you some more detail into what Quadrant2 is all about. It's a platform that we developed at Patheon where we look at the API and look at the input of the API based on your business objectives as well as the physicochemical properties, and we make a technology recommendation. We've developed a technology selection tool for polysoluble compounds, which I'll go into further detail in a bit. Based on that, we select the technology, and then we do some more molecular modeling, which again my colleague Matt Wessel will go into in depth in the second half of this talk. And we nominate a drug product intermediate leading to a drug product development program, eventually clinical trial materials, and hopefully commercial drug product. So this whole approach is what we call as Quadrant2. The basis of this is the molecule, and our belief is that the API has to determine which technology would work, and based on that, how do you go about selecting formulation for your technology. So as I mentioned, structural analysis is important, molecular model is important, modeling is important, and informed experimentation definitely is key. So it's a multi-pronged approach. The advantage of this is you're not guessing, you're not relying on empiricism, you're actually using a rational strategy to formulate polysoluble compounds. So what I'm showing you here is a formulation space characteristics of polysoluble compounds. These are the various technologies that people are using in the industry. These are very well known. So what we've done here is created a map of the various technologies showing the formulation complexity and the breadth of applicability. The reason we did this was we wanted to develop a technology selection tool based on the complexity of the formulation and the breadth of applicability and the API physicochemical properties. So the output of this technology selection tool, and there's a poster that I just presented half an hour ago. You're welcome to copies for that. The output of the technology selection tool is you get a rational way to select which technology has a good probability of working. For example, for this molecule, dipyridamole, the technology selection tool is predicting that spray drying and hot melt extruded amorphous dispersions have a good probability of working. Some of the input that went into this algorithm of the technology selector is shown in this slide here. So we look at things like lipid solubility, chemical stability, partition coefficient, aqueous and organic solubility, melting point, TG of the drug and polymer, and dose. So these are the different factors. We put inputs on the factors as low, medium, high into the algorithm in order to give us an idea of which technology has the high probability of succeeding. And we actually published an article in Drug Development and Delivery, how to choose the right solubilization technology for your API in last year. You're welcome to look it up. So once you develop this algorithm, how do we know it works? So any model you develop, you need to validate it. So what we did was we looked at commercially available products in the market. This slide is showing you 3 different drugs: noxafil, rocaterol, and itraconazole. They all have very similar log P and log S. In other words, the solubility and the permeability characteristics of all 3 are very similar. So which technology would work? How do you go about starting to pick? So our technology selection tool actually discriminated for each of these. For example, for noxafil, we predicted that dispersions by spray drying or hot melt extrusion would work. The commercially available product is a hot melt extruded product. For rocaterol, we predicted in the middle, the green, all those technologies have a good probability of working, and indeed lipids is the commercially available technology for rocaterol. For itraconazole, we predicted spray dried dispersions or hot melt extruded beads, or hot melt extruded dispersions or coated beads would work. And indeed, Sporonox is a commercial product, itraconazole by Janssen, and that is a coated bead product which is commercially available. And the next generation of that was Onmel, which is a hot melt extruded product. So we successfully predicted that compounds which have similar log P and log S indeed can have different routes to commercialization. And it all depends on all the factors that I mentioned earlier and what we input into the model. Some more analysis of commercially available products. There's a spider plot which shows about 70 products were analyzed. About 90% of these products that are commercially available, our predictor successfully predicted that particular technology which is being marketed. So I'll switch gears a little bit and now switch into more of the nuts and bolts of Quadrant2. I'll give you an introduction, and Matt Wessel will talk into the more of the technical details. So as we all know, I'm going to focus on amorphous spray dried dispersions particularly for this topic. So as we all know, formation of a spray dried amorphous dispersion involves dissolving a drug substance and typically an organic solvent along with a polymeric excipient, and you end up spray drying it. So you end up getting a spray dried intermediate which is amorphous in nature. So what drives this from a molecular to a thermodynamic level? And that's what we set out to. Our goal of Quadrant2 is intended to target the understanding at a deep molecular level to a thermodynamic level. There's a wide variety of excipients, as you all know. There's a broad selection of different polymeric excipients. We also have a even broader selection of surfactants and lipidic excipients. So given the universe of all these excipients, where do you start? So this is what we achieve by using our Quadrant2 approach, is we computationally screen drug and excipient combinations and narrow it down to a few leads, 2 to 4 leads, maybe 4 to 6 leads out of almost 100 excipient drug polymer combinations. Instead of empirically determining it, we computationally select the leads. What's the advantage of this? Is it's much more efficient as opposed to empirical screening. It enables broader analysis quickly in silico, and this would not have been possible without the advances in computational software as well as computational computing power, if you will. This wouldn't have been done maybe 20 years ago, but now we all carry complicated computers in our pockets, right? So this is basically a direct outcome of where we are in terms of computing power. Some of the things we do is look at the single crystal structure, look at quantum mechanical models, molecular dynamic models, look at phase diagrams, look at create some excipient descriptor databases based on the API structure and the excipient structure. Things like what I'm showing you here is a classic ball and stick approach on the left, bottom left. This molecule is dipyridamole. It's a polysoluble compound. We assign various descriptors, as I'm showing you in the middle of the bottom row. We look at potential energy surfaces. These are like sticky points to a molecule, if you will. It's very similar to a drug binding in a protein pocket. We have used that approach in formulation design. That's the closest analogy that you can keep in your head. So same thing we do with various excipients. Look at similar descriptors that would work, that would fit with a molecule. So in other words, essentially what we're doing is matchmaking a drug with the excipient which would give it the desired attributes. We do molecular dynamics simulations. Matt will go into details shortly. Now what I'm showing you here is solid state molecular dynamic simulations of dipyridamole and polyvinyl acetate phthalate. That's a enteric polymer. You're looking at the space filling, the blob, the gray blob that you see, that's the polymer, and the blue and the red are the active dipyridamole molecules. And then we can also model a dissolution in water and how the drug and the polymer dissociate. These are all done at computational times of few nanoseconds. These are all iterations done at the picosecond steps. So computationally they take a few hours to days. So we get insights into how a drug and an excipient would behave both in the solid state and the solution state. And before I end, these are the typical output of a molecule. For example, if I'm working with a client molecule, when we do our modeling, we do the rank ordering and we pick a handful of lead excipients. In this case, for dipyridamole, the modeling approach shows that those 5 polymers that I'm showing on the right of the screen here, HPMCP, HP55, HPMCASM, PVAP, PVPVA, Soluplus, those 5 have a high probability of succeeding as an amorphous dispersion polymer. With that, I am going to turn over the rest of the presentation to my colleague, Matt Wessel. Matt?
All right, thanks, Sanjay. So I'll talk a little bit about the molecular modeling in a lot more detail. What you see here is a slide that describes the problem that we're actually trying to solve. So in a solid dispersion situation, we're taking this crystalline drug here and we're mixing it with an amorphous polymer to form this amorphous dispersion where all the drug molecules ideally would be individually dispersed within that polymer matrix. And we do that obviously by either melting or dissolving the drug in a solvent or melting it, hot melt extrusion, etc. Now you can see that a dispersion is really only as good as the thermodynamics that govern that dispersion. So if the free energy of the dispersion is negative, well then that dispersion would in theory be infinitely stable. If the free energy is not negative, then you've got a kinetically trapped situation, okay? What we do to understand this is actually molecular dynamics simulations. And since that's my background is in computational chemistry, I've brought that technology and that science to Patheon to try to help us better understand how these dispersions actually go forward. We can do small scale molecular dynamics simulations that you see here. Typically we do that on a smaller computer, but we actually can then leverage the cloud to do large scale computations with many more atoms in the simulation to get much more accurate results. And that's what you see there. This is an actual dispersion of a drug. I think this is nifedipine in a PVP polymer, and so that's just an image of what that actually looks like after a full molecular dynamics simulation run. So you can actually see here that what you have, and it's 25% loaded by weight, by the way, what you have are regions of drug agglomerates, as well as many regions where the drug is actually individually dispersed within the polymer. Yet these things still work, and so we have to understand that from a thermodynamic perspective. What we're actually simulating is the following physical situation. If you take, say, a drug like nifedipine as a crystal and PVP as your polymer, the first thing you have to do in order to get these to mix in an experimental setting is add in your heat of fusion. This is the energy it takes to melt the crystal. So you would melt the crystal, form nifedipine liquid, which would then mix with PVP. And then what you would see is that the energy it takes to actually melt the crystal would be either less than or greater than what you measure in your experiment, because if it's less than what you measure, what that means is that you have to add even additional energy in order to get the situation to mix intimately. However, if the actual energy is less than the energy it takes to melt the crystal, then you've got favorable interactions in your dispersion. And you can actually measure this experimentally with DSC, and we've actually done that. So what we're trying to simulate is this energy plot here, where you see crystalline nifedipine and PVP at some low energy level here. You add in your energy. If it's amorphous, you would add in your transition energy heat. Otherwise, your heat of formation, or heat of fusion, should I say. And then you would see a heat of mixing that would occur. These are these excess heats of mixing that you often see in liquid-liquid systems, such as ethanol and water, where you know that if you mix ethanol and water, you actually get heat out of the system and the volume decreases of the final solution because it's non-ideal mixing. So that's actually what you see. So we're trying to understand, can we simulate and understand what the energy value is? And it turns out that we actually can, and do it quite well. This is what one of these simulations actually looks like when you look at this as an end result. What you see in red is the polymer, and in green is the drug. I didn't choose it because it was Christmas colors. That's just, they contrast well. But Christmas is right around the corner if you need to do some shopping. So the density is about 1.062, which is reasonable for these simulations. Typically, these dispersions have densities of 1.1 to 1.2 grams per milliliter. We're getting about 1.062. We think we know why this is, and I've already examined ways of correcting that so that we actually get accurate densities. That's a 10% loaded dispersion. That's what it looks like. You can see even at 10% loading by weight, you've got some drug agglomeration going on. It happens a lot in these dispersions. So this is what we're simulating. We're simulating this mixing event, okay? Now you look at some different loadings, 10% loaded, 20%, 30%, and you can see that the green here in the 30%, you're starting to see even more agglomeration. Now that's for this particular system, which is nifedipine and PVP. Here, you actually see how the density changes, and it's linear, as you would expect. The density goes between that of pure PVP and that of pure nifedipine, which is exactly what you would expect. And these are directly out of the simulation. What's interesting, and I find fascinating, is that if you look at the excess energy of the pairwise energy, which is electrostatic energy, so charge interactions, and van der Waals interactions, ideally you would have this straight line increase, but you don't see that it's ideal. It's non-ideal. Just like a lot of things that mix, very non-ideal in nature. We can simulate this. In fact, that is simulation data right there. We can also measure this experimentally, as I showed you with the heat of mixing experiments that I talked about. If you look at this information in a plot, you start to see that we're actually accurately simulating things pretty well. We don't have the magnitude of the energy values correct yet, but we have the shape of the curves right. On the left is simulated data. This is from molecular dynamics simulations. On the right is experimental data for the same system. So using the heat of fusion and the melting enthalpy with DSC experiments, you see this sort of non-ideal behavior. The red and the blue are just the differential heats, and so what you really care about is the differential heat of solution of nifedipine in pure PVP, which is about 58 kilojoules per mole, or joules per gram. And for PVP, so if you take 1 gram of PVP and put it in pure nifedipine, you'd get back about 127 joules per gram. If you look at the simulations, we're actually well within an order of magnitude of that. In fact, pretty close to that. And I think if we improve the charge model and the van der Waals radii of the atomic nuclei within the simulation, we'll actually see these values start to approximate what we see over here. Another thing to consider is that we run these at 300 Kelvin, or room temperature. These have to be done at higher temperature, which has an impact on the thermodynamics. You'll see actually larger energy numbers that if you back calculate to room temperature, which we would need to do, we haven't done that, you would probably see these numbers start to decrease. So we think we have a very, very good model for actually being able to accurately predict these things using MD simulations. This is kind of what these things look like inside. This is a 30% loaded dispersion. Again, I think the drug here looks like this is actually dipyridamole in PVP, and you can see as we slice away with this graphics visualization software that we use, you can actually see kind of what these things look like inside. And so you see the drug is the green blobs, and inside, if they're cut away, is the orange stick figure of the actual drug. And then sort of the diffuse stick figures that you see outside of that, that's the polymer. And so that's what these things actually look like. And you can actually get an accurate pictorial representation of what these dispersions look like, whether it be hot melt or spray dry. One point I'd make about the difference between spray dry and hot melt is that we do know that the same system, same drug, same polymer, whether you make the dispersion with hot melt or whether you make the dispersion with spray dry, you'll get different dissolution behavior, which tells us that probably in the spray dry case, since we're dissolving everything in a solvent, we have a much more homogeneous system than you might see in a lot of hot melt extrusion experiments, which is another advantage we think spray drying can offer. So we think we've got a very useful approach for simulating the stability. The next step is to simulate dissolution. So we take these amorphous dispersions that we've simulated, we add water, we run additional MD simulations and try and understand what do these things look like as they dissolve. And can we use that information to help us predict behavior in vitro, which ultimately with IVIVC, we would be able to predict in vivo. So the next step is solving this problem where you've got this very complex arrangement of kinetics and thermodynamics where you've got a solid dispersion, you add water, you immediately start to see supersaturated free drug, but it's also going to be in partition with polymer and solution, and the extent to which that occurs depends on the drug and the polymer and the nature of those two. You also will see crystallization either directly from the colloidal suspension or from the supersaturated state. You also see agglomerates which themselves can move towards crystalline. All of these things are in equilibrium with each other, and the key is that I'm not showing the other sink, which is saturated free drug going into the lumen and getting absorbed. Okay, so that's what we're trying to do, is maintain that saturation state so we can get drug absorption. And if that can compete better than all of these other phenomena that aim to reduce the supersaturated state, then we've got an effective dispersion that can actually potentially become a product. So in conclusion, we're really taking things from a two-dimensional structure, in fact even a one-dimensional structure of the drug molecule, in this case this is nifedipine, and PVP, run small-scale MD simulations, use that to predict the thermodynamics and do excipient selection if in fact it's going to be a dispersion, and then run large-scale simulations to get much more accurate thermodynamic information about this. And we've got very good agreement with experiment. We're continuing to press this method forward, advance the method, improve the charge models, improve the other characteristics of the modeling, and take this forward. So with that, I'd like to finish and acknowledge Marshall Crew, who's I think right around the corner there, maybe not. Tom Reynolds, who's my office mate back in Oregon, where I'm from, Bend, Oregon. And that's contact information for Sanjay and myself. And with that, I'll conclude and answer any questions you might have.